It says convert a pressure of 431 torrs to atmospheres. Now, the conversion factor that we're going to use for this is actually on your formula chart. It's where it says 1 atmosphere equals 760 millimeters of mercury, which equals 101.3 kilopascals. Okay, and you might be thinking, well, torr's not on here. Torr is the same thing as millimeters of mercury. So all we got to do is we got to box what we're dealing with, these guys right here. So there's our conversion factor. 1 atmosphere equals 760 torrs, or millimeters of mercury. It's the same thing. Remember, with any conversion, we start with the number in the problem. So we start with 431 torr. And whatever's on top goes on the bottom. So we're going to go ahead and put our 760 torr on the bottom and 1 atmosphere on the top. And we go ahead, multiply this out, and then divide, so basically be 431 divided by 760, and we should get an answer of 0.567, and the unit would be atmospheres. Okay, moving on to number 3. It says a sample of helium gas has a volume. It gives us a volume of 269 milliliters at a pressure of 0.62 atmospheres. What pressure is needed to reduce the volume at a constant temperature to 58 milliliters? Now, because it said constant temperature, I know that I'm going to be dealing with Boyle's law, which Boyle's law, if we remember, we don't have to know all the laws, but if we know our combined gas law, P1V1 all over T1 equals P2V2 all over T2, and if temperature is constant, we just take it away, and there's Boyle's law. Okay, and Boyle's law is going to be our P1V1 equals P2V2. And we're solving, it says what pressure is needed, so we're solving for the second pressure, solving for this, so we divide by what's beside it, we divide by V2, and we get our equation where we get P2 equals P1 V1 all over V2. Okay, so all we have to do is plug this in. Now, we know that this is going to be our V1 because it's our first volume that we see. This is our P1 because it's our first pressure we see, and we're changing it to, so this is our V2. So we go ahead and plug everything in. P2 equals our 269 milliliters times our, that's our V1 times our P1 of 0.62 atmospheres, all divided by our 58 milliliters. Okay, and what we'll see when we plug this in the calculator, make sure that you put parentheses around the numerator and parentheses around the denominator. Don't put them around each number, put it around the entire numerator and the entire denominator, and we should get an answer right around 2.88 atmospheres. Okay, number 5, it says use Boyle's law to find V2 given, and it already gives us our P1, V1, P2. So our equation for Boyle's law we know is P1, V1 equals P2, V2. And if we're solving for V2, we have to divide both sides by P2, and we get V2 equals our P1, V1 all over P2. Which we go ahead and we plug in what we have that's already given to us. It's our 377 torr and our 116 milliliters for our V1 all over our P2, which is 743 torr. And make sure we put parentheses around the numerator and denominator. Plug it in the calculator, and we get an answer of 58.8587 milliliters. Okay, number 7, it says use Boyle's law to find P1, and it gives us all of this. So remember our equation, P1 V1 equals P2 V2, and if we're solving for P1, we'll divide both sides by V1, and so we get our P1 equals our P2 V2 all over V1. Main thing here is just making sure we keep everything in the right order. So here we would have our P2, which is 182 millimeters of mercury, and our V2, which is 2.5 times 10 to the third milliliters, all divided by our V1, which is 3.3 times 10 to the fifth milliliters. Now remember, scientific notation, we use second comma to get that E, and when we plug it in, make sure that we put parentheses around the numerator and the denominator, and if we do that correctly, we should get an answer of 1.38 millimeters of mercury for our initial pressure. Alright, number 9, it says at 125 degrees Celsius, the pressure of a sample of nitrogen is 1.3 atmospheres. What will the pressure be at a temperature of 203 Celsius, assuming a constant volume? Okay, so when we're working this one out, it's a Gay-Lussac's problem because we know that we don't have a constant volume. So Gay-Lussac's equation is P1 all over T1 equals P2 all over T2. Okay, and we look and see what we have. We have our initial temperature, or T1. We have initial pressure, which is P1, and then we have a secondary temperature, which is T2. And it says, what will the pressure? So we're searching for our secondary pressure, which is P2. Now remember, anytime that we get a fraction like this, go ahead and cross multiply. So we have our P1 T2 equals P2 T1, and we go ahead and divide both sides by T1 so we can get what we're solving for, and so we get this equation where we have our P2 equals our P1 T2 all over T1. Now one thing that we have to make sure that we do here is we convert our temperatures into Kelvin, because we can't do any math unless it's in Kelvin. So all we do is we add 273 to them. So our initial temperature, our T1, after we add 273 to it, is going to be 398 Kelvin. And when we add 273 to our 203, we will get a temperature of 476 Kelvin. Okay, so now that they're in Kelvin, we can go ahead and plug everything into the equation. Our initial pressure is 1.3 atmospheres, and then our T2 is going to be 476 Kelvin, all divided by our T1, which is going to be 398 Kelvin. And we plug, remember, parentheses around the numerator, denominator, and plug all this into the calculator, and we get 1.55 atmospheres for our secondary pressure. Okay, on number 11, go ahead and work this one out. It says a gas occupies 69 milliliters at standard conditions. Okay, now remember, standard conditions means standard temperature and pressure, or STP, which means that the temperature is going to be 273 Kelvin, and our pressure, since this pressure is in atmospheres, we're going to go ahead, and our standard condition means that we have 1 atmosphere of pressure. Okay, and it says that that gas is heated, so it heats up to 24 degrees Celsius. Now remember, we have to change that into Kelvin, so we're going to go ahead and add 273 to it, and we get this temperature, which is of 24 degrees Celsius, is now going to be 297 Kelvin. Okay, and it says, so it's heated up to 297 Kelvin, while the pressure is reduced to, so we have a new pressure right here. It says, what is the new volume occupied by the gas? So in this, we have pressure, temperature, and volume, so we are going to use the combined gas law, which our combined gas law we know is P1 V1 all over T1 equals P2 V2 all over T2. Okay, remember, once we get fractions, let's go ahead, cross multiply, so we'll get P1 V1 T2 equals P2 V2 T1. Okay, and it says, what is the new volume? So it's looking for our V2. So we go ahead and we divide both sides by what we're looking for, or what's beside what we're looking for, and we get P2T1. Okay, so this is going to be our equation because these guys are going to cancel out. Okay, now what we want to do is we just want to plug everything in now. So here is our initial volume, or our V1. We know that 273 is going to be our T1, and this is going to be our P1. And then this new temperature is our T2, and this new pressure is our P2. So we go ahead and we plug everything into our equation. We have our initial pressure of 1 atmosphere times our initial volume of 69 milliliters times our T2, which is 297 Kelvin, all divided by our P2, which is 0.92056, times our T1, which is 273 Kelvin. And remember to put parentheses around numerator and denominator. Go ahead and plug that into the calculator, and we should get an answer right around 81.5438, and that unit would be milliliters. Alright, moving on to number 13. It says an aerosol can contains gas under pressure of 4.6 atmospheres at a temperature of 19 degrees Celsius. Now we got to change that to Kelvin. So we go ahead and add 273, and that temperature is now 292 Kelvin. It says if the can is left on a hot sandy beach and the pressure of the gas increases to 4.82 atmospheres, what is the Celsius temperature of the beach? Now you might be thinking, well, why didn't I just leave it in Celsius? Well, you cannot do math in Celsius. You have to do math in Kelvin. So when we're finished with this, what we're going to end up doing is subtracting 273 from it to get the Celsius temperature. Now the equation that we're going to be using is our P1 all over T1 equals P2 all over T2. Remember, cross multiply here and we get P1 T2 equals P2 T1. Okay, and we're solving for our secondary temperature, so we'll divide both sides by P1. Okay, to solve for secondary temperature. Now this written out, so we have T2 equals P2 T1 all over P1. Okay, so when we're working it out, plug everything in. Our secondary pressure, which is 4.82 atmospheres, times our initial temperature, which is 292 Kelvin, all divided by our initial pressure, which is 4.6 atmospheres. Okay, when we go ahead and we work this out, we get an answer of 305.965 Kelvin. Now remember, it wants it in the Celsius temperature, so we go ahead and subtract 273 from it, and we should get a Celsius temperature of 32.9652 degrees Celsius. Okay, moving on to number 15. It says, what is the molar mass of a gas if we have 0.437 grams of the gas occupies a volume at 136 milliliters at 30 degrees Celsius and 1.13 atmospheres. Okay, main thing with this is we have to make sure that we have the correct units. We're going to be using a version of the ideal gas law. The equation we're going to be using is molar mass equals mass times the ideal gas law constant times our temperature all over our pressure times volume. Okay, now when we're using this, we have to make sure that our mass is in grams, which it is. R is always going to be 0.0821. Temperature has to be in Kelvin. Pressure has to be in atmospheres, which it is, and volume has to be in liters. It's in milliliters, so to convert from milliliters to liters, we divide by 1,000, and we get our 0.136 liters. Okay, so making sure that we have all the correct units, we can go ahead and plug everything in. So we have 0.437 grams. times our ideal gas law constant, and you can find the ideal gas law constant on your formula chart. It's labeled as R. Times our temperature. Remember, temperature, we need to add 273, so we get a temperature of 303 Kelvin, all divided by our pressure in atmospheres of 1.13 atm, and a volume, which we changed to liters, of 0.136 liters. Remember, parentheses around the numerator and the denominator. Plug this in, and we should get a molar mass of 70.488 grams per mole. Okay, moving on to number 17. It says a gas sample occupies, and it gives us 8.5 liters at 48 degrees Celsius. What is the pressure given that there are 1.09 moles of a gas sample? Now, in this, we know that we're using the ideal gas law because it doesn't give us two volumes or two temperatures, and we're dealing with moles. So ideal gas law is PV equals nRT, which is just Pivnert. Okay, and we're solving for, it says what is the pressure. So we're solving for pressure, so we divide both sides by volume. Okay, and we get pressure equals our moles times our ideal gas law constant times temperature divided by volume. Make sure that we have everything in the correct unit. We need liters, atmospheres, moles, and kelvins. We're solving for atmospheres, so we don't have to worry about that. We just need to make sure we have liters, moles, and this temperature needs to be in Kelvin, so we add 273 to it, and we add 273, we get a temperature of 321 Kelvin. Okay, so we plug everything in. Our moles is 1.09 moles. Our ideal gas law constant, remember it's on our formula chart, it's 0.0821 times the temperature of 321 Kelvin, all divided by a volume of 8.5 liters. We go ahead and plug this into the calculator, put our parentheses, and we would get an answer of 3.37953, and the unit would be atmospheres. Okay, moving on to number 19. It says the phase diagram for a pure compound is given below. Okay, and it says the triple point occurs at where? Now, realize that when we're looking at this things we need to know, we have solid, liquid, and gas, and this represents, it's a pressure in atmospheres and a temperature in Kelvin. Up here, we call it our critical point. It's up here, and then our triple point is going to be down here. And depending on pressure and everything else, the pressure will tell us at what temperature it changes from a solid to a liquid, and from a liquid into vapor. It'll give us our normal boiling points and normal melting points. Okay, but in this case, we're just looking for the triple point, and that's where all three phases of matter occur, which is right here, which is at 50 atmospheres and 200 Kelvin. Okay, here is number 21. It says the solids sublimes, and it wants to know at what pressure and temperature it sublimes. Now, sublimation is when it moves from a solid straight into a vapor. So if we see that we're looking at this, if we're at a pressure of 150 atmospheres and we're moving across, we see that we'll hit the liquid phase. Okay, now sublimation means that it skips the liquid phase. It doesn't go in the liquid phase. So if we look at anything below 50, what happens is as we're moving across, it moves straight from a solid into a vapor. Okay, so this would be sublimation. So anything below this 50 atmospheres of pressure, we're going to have sublimation. Okay, it says choose a state of water in which the water molecules are farthest apart on average. Main thing that we have to look at with water, water has a special property where in the solid state it's actually less dense than in the liquid state. But in this case, it's giving us all three states of matter: steam, liquid, and ice. And we know that any gas of a substance is all the molecules are very, very far apart. They're moving very quickly. So the correct answer would be number 1. Let's just keep in mind that if it didn't have the steam as an option, we would have to pick ice, because ice is actually the molecules are farther apart. On number 25, it says a piece of copper alloy with a mass, and it gives us a mass of 65 grams, is heated from 32 degrees Celsius to 43 degrees Celsius. In the process, it absorbs 502 joules of energy as heat. It says, what is the specific heat of the copper alloy? So when we're working with specific heat, we know that the equation is Q equals MC delta T. Now Q is always going to be our energy or our joules, M is mass, C is actually our specific heat, and delta T is our change in temperature. Okay. Which change in temperature means final minus initial. So when we're solving for this, our specific heat is going to equal our Q, all divided by our mass times our change in temperature, which when we go ahead and we plug this in, we have a Q value of 502 joules all over a mass of 65 grams times a change in temperature, and when we do our 43 minus our 32, we get a change in temperature of 15 degrees Celsius, or degrees Celsius or Kelvin, either way, it's just a change in temperature of 15 degrees. And we go ahead and we plug this into our equation, and we see, and that's actually not 15 degrees Celsius, it should be 11 degrees Celsius. But we plug this into our equation, plug it into our calculator, and we get a specific heat value of 0.702098. And the unit for specific heat looks a little weird. It's joules, grams, times Kelvin.